When do you multiply probabilities? Here's situation number one. We're going to take 2 balls from the pot without replacement. So there's 2 white and 1 black marble. A ball is randomly selected from the pot and not replaced. So you hold it in your hand. A second ball is then drawn. Define the following events. Event A, first ball is white. Event B, second ball is white. Find the probability of A. Okay, how many balls, how many marbles are there in the pot? Grand total. Yeah, be obvious. Jake, how many are white? So what's the probability that the first ball is white? Don't overcomplicate it, right? Okay. What's the probability of B, the second ball, being white, given that the first ball is white? So now what we have is this. Don't write this next bit down, but Kyle, you're holding this in your hand. How many marbles are left in the pot? 2. How many are white? So we would write this. The probability of B given that A has occurred, the probability that you get the second white given that the first one was white, 1 out of 2. I'm going to unerase that because I want my diagram back. The real question is, okay, what's the probability of A and B occurring? Getting 2 whites in a row. The best way to answer this or to visualize this is with what we call a weighted probability tree. I sketched it out, but I left it all blank. There's the tree. So we have on the first ball, it could be white or not white. And when I type these notes up, we use the bar for not. You can use the bar or the apostrophe. Both of them, Chelsea, mean not. Okay? What did you say, Jake, that the probability of getting a white ball was? We put that weight on the actual branch itself. By the way, do the math. What's the probability of getting a black ball on the first draw? 1 out of 3. If you have your tree set up right, Logan, there's a built-in error check. These should always add to 1. Do they? You didn't miss anything. It's a quick glance error check. Then on the second ball, it could be white or black, white or black. Down this branch, Darian, we got a white ball already. How many white balls are left in the pot? Out of? What's the probability, if you get a white ball first, what's the probability of getting a black ball second? Also 1 out of 2. By the way, double check, do those add to 1? We didn't miss anything. Down this branch, you picked a black ball. So that means this one is no longer in the pot. How many balls are left in the pot? 2. How many are white? What's the probability of getting a black ball given that you've already picked a black ball? Double check. Do those add to 1? Okay. There's the tree setup. You want the probability of A and B. It's going to be calculated by going no calculator yet. Top times top, 2 times 1. Anyone? Over 3 times 2, 6. And I know in lowest terms that's 1/3. I don't care. Okay. Then it says events A and B are dependent because I'm going to leave that blank for a second and come back to it after the next example because I want to compare both of these. Situation 2 is identical to situation number 1, except this time you're putting the ball back in after you pick it and shaking the container up again with replacement. Okay. What's the probability of getting a white ball on the first draw? Still 2 out of 3. Nothing's changed there. So you get a white ball. Now you put it back in, Mac. You shake it up. What's the probability of getting a second white ball? I can't hear you. You're right, I think. 2 out of 3. We would say this. The probability of B given A in this case is 2 out of 3. Then it says A and B. Pam, let's come back to that. Let's fill in the tree. So here's what we have on this tree. We have 2 out of 3, 1 out of 3. Double check. Do they add to 1? I got everything. But then, Taylor, we're putting the ball back in. So it's going to be 2 out of 3, 1 out of 3. What about on the right-hand branch? You picked a black ball. You put it back in. You shook it up. So how many balls are left in there now still? 3. How many are white? Double check. Do they add to 1? Double check. Do they add to 1? So didn't miss anything. Okay. What's A and B? Let's multiply down the branch, which is top times top over bottom times bottom. 4 over 9, not 6. Every once in a while I have a kid. 6, 9. Is that okay so far, Brianna? And now I want to talk about, to me, the best way to figure out whether events are dependent or independent. It's not the most wide-ranging way. It's not the most flexible way, but it's the best way. What can you tell me about these 2 branches and these 2 branches? They are the same, because it turns out it doesn't matter what you got on the first draw. It didn't change the odds on the second draw. What can you tell me about these 2 branches compared to those 2 branches? They are different. Why? Apparently, what you got on the first draw affects the probability of what's going to happen on the second draw. That's the definition of dependence. What happens earlier affects what happens later. Okay? So there's several ways to define this or fill in the blank. The way I like the best, the easiest, the most visual is A and B are dependent because the bottom branches are different. Brianna, this B and this B have different values. Both B's, they're both second ball white, but apparently it depends which side you went down. A and B are independent because bottom branches are identical. Wait a minute, Mr. Dueck. One's a 2/3 and one's a 1/3. What I really mean is the bottom groups of branches are identical. It's a 2/3, 1/3, 2/3, 1/3. Okay? But I haven't figured out a short way to write that without going into long. Kids figure it out. That's not the mathematical definition. Okay? The mathematical definition is this. P of B changes depending on whether A occurs. Did A occur? Then the probability of getting a white ball is 1/2. Did A not occur? Then the probability of getting a white ball is guaranteed. Caught you again. Maybe one more Coke. I had to. I'm tired too. Oh, and A and B are independent because isn't affected by whether A occurs. That's the English definition, and now I have a mathematical definition. So go back up one again to the top here. I think I left you enough room. I hope I left you enough room. Do you know how you know they're independent? The probability of B, if A occurs, is the same as, is different from, is not the same as the probability of B given not A. That's the shortest way to write it. It's also all formulas and symbols, but here's what it's saying. You know what? B is not the same, depends which branch you went down on A. Here, probability of B given that A has occurred is the same as the probability of B given that A has not occurred. Doesn't matter. Mark, there's another way to do it, and that's intuitively. Another way to do it is intuitively. Please tell me I still have it. Yeah, I do. Coin. Let's suppose I flipped it and I got 9 heads in a row. What are the odds of the 10th one being heads? Still half and half. What happens before has no effect on what happens after. Rolling a dice, same idea. You roll 3 ones in a row. I'm telling you, the odds of rolling a 1 on your 4th is still 1 in 6. Still 1 in 6. Picking a card. Ooh, where's my deck of cards? Give it a quick shuffle. Hold this, don't look at it. What's the probability that this is an ace? Okay, there's 51 cards, but I'm going to tell you, doesn't it depend? It depends on whether or not Ben is holding what? See, if he's got an ace, how many aces are left? 3 out of 51. If he doesn't have an ace, 4 out of 51. Picking cards, if you're not replacing the cards on each pick, cards are dependent. That's why it's so tough to keep track of 5 or 6 or 7 cards and the probabilities. Not an ace. Turn the page. So here is the multiplication law. It says this. And means times. So A and B is multiply times. Please make sure you go down the B branch where A has occurred. In other words, Pam, don't go this times that one. Even though that's a B, you've gone down the wrong branch. The probability of A and B is multiply. It's the probability of A times probability of B, assuming A has occurred. Oh, and by the way, you can rewrite this. Sometimes you'll see them, what's the P of A doing to this here? Timesing, so how could you move it over? Sometimes you'll see it rewritten like this. This is an equivalent formula. In fact, this one here is going to become really important later. Don't put a box around it right now. It's going to become really important later to do something called conditional probability, which is very counterintuitive. This is what that there is where I can explain perhaps how to save your life. I can explain, sadly, why racism will always be present. I can explain why you can't use a polygraph in a lie detector in a court of law. I can explain a lot of stuff from that little equation there. I can explain why OJ, had they had a mathematician on the prosecution's trial staff, would have probably been convicted of murder the first trial and not been found innocent from that little equation there. But we'll get to that in a few days. What's the special subcase? They're independent if the probability of B given A, you know what, is just the probability of B. It doesn't matter. Darian, they're independent if it doesn't matter which branch you go down. B is B is B is B is B is B is B. As opposed to here where B and B are not the same. Is that okay, Sterling? Yeah. In which case, but here's what I want you to notice, Connor. In both of them, you know what and means? Multiply. I did it, Carson. I've been doing so good. Wow. Hang on, we got to pause here because I've promised myself. 2 cards are drawn. How many cards? I'm probably going to do a tree then. This is different from last day when I said how many cards? 1. We could count and use formulas, and we could use or means add minus the overlap. 2 cards, I'm going to do a tree. Now, here's the other key thing. We're not going to be putting the card back, which means the odds are going to change each level. Okay? We're going to define the following events. Event A, the first card is a face card. Event B, the second card is a face card. How many cards are we drawing? 2. How many levels will my tree have? 2. Okay? I'm going to have this. A, not A, B, not B, B, not B. And I'd like you to put your pencils down, but pay attention for a second. Give Ty an elbow. Okay, then look up. Because I'm going to do this next bit symbolically, and then I'm going to erase the symbols, and what you're going to put in there is the numbers. Symbolically, here's what we're saying. The number that's going to go here is that. The number that's going to go on this branch is that. The number that's going to go right here is the probability of B given that A occurred. The number that's going to go here is the probability of B given that A didn't occur. Oh, and you know what? This branch is the probability of not B given A occurred. This is the shorthand symbolism that I can use to tell you what sub-branch we're on. This branch here is the probability of not B given what? What do we know? What branch did we go on up top? That's the symbolism to describe each branch. But I'm going to erase that. We're just going to put the numbers in instead, because I think numbers are a little clearer. So pick your pencils up. A face card. How many face cards are there in the deck? 12 out of? How many non-face cards are there in the deck? Please don't count. Please use the complement. 40 out of 52. Double check. Does it add to 1? I got them all. Down the left-hand branch, you picked a face card. You with me, Brianna? Or are you zoning out? You with me? Okay. So how many face cards were there initially? 12. You picked a face card. How many are left? Don't overcomplicate it. How many were there initially? You picked a face card. How many are now left? Out of? Why 51? Why no. Why 51, folks? Because you've already picked a card. Okay? So down this branch here, how many non-face cards are there? 40 or 39? Down this branch, there's 40 left because you didn't pick a face card out of 51. Double check. Do they add to 1? Check. Down the left-hand branch, ka-choom, you picked a non-face card. So how many face cards are left in the deck? Out of 51. How many non-face cards are left in the deck on this second level? 39 out of? Double check. Does it add to 1? Yeah. Hopefully, by the way, you're spotting that double check. It's a really handy, quick error check. I've got my tree set up correctly. What do they want me to find? Determine what? A and B. Multiply down. Don't circle it because it's going to clutter up the diagram. But this is the branch we're talking about, Brianna. It's going to be 12 out of 52 and 11 out of 51. Top times top, bottom times bottom. I know 52 times 51 is 2652. I've memorized that over the years because it shows up so often. 12 times 11 is 132. Double check me. Oh, and you can reduce that to lowest terms if you want. What is that in lowest terms? Don't all rush for your calculators at once or anything.
11 over 221.
11 over 221?
Yeah.
Now, here's why I like this as well. I don't know if you remember at the very beginning of this, Mark, before Christmas, I said all of us are good at very basic probability, and we suck as soon as it gets anything past basic. This is 2 cards. This is the same type of card twice in a row. If I had asked you to make a prediction with the denominator, nobody would have said, oh, it's going to be out of 221. Right? That's not what leaps to mind. You might think it's going to be out of 52 or out of 51 or something, but not out of 221. Oh, and 11 out of 221. And Zach, this is only 2 cards. This is why people are so bad at gambling. The intuitive approach to this, Ashley, you're not going to get the right answer. Oh, by the way, now that I have that tree, you'll do enough trees that you'll get good enough sterling that it'll take you 20 seconds to write a tree. But now I can answer anything. Part B says, not A and B. Okay. Not A. What's that?
Not A is
40 out of 52. And B. Go down the right B. Don't be telling me 11 out of 51, because that's not the correct B. We want the B from the not A side, which is?
12 out of 50.
There's the probability of not getting a face card on the first draw and then getting a face card on the second draw. It's going to be 480 out of 2652. $480 out of 2652. Math, enter, enter. Is it 40 out of 221?
Yes.
Hey, what if I asked you, what's the probability of getting no face cards? Which 2 numbers would you multiply there?
40 over 52.
40 out of 52 and times 39 out of 51. What if I said, what's the probability of getting only one? Oh, let's come back to that. Only one face card. Well, would be this branch. Nope, that's 2 face cards, Mr. Dueck. Exactly one would be this branch or this branch. What does or mean? You'd find one branch plus multiply down, find the other branch. There is no overlap, though. We set this tree up so that nothing can happen at the same time. You know how I know? Because we use the complement trick every time to fill in the missing branches. That's why trees work well as well. Okay, turn the page. About 10 more minutes. Suck it up, Buttercup. You'll be fine. It's kind of cool. You learn how to gamble. Well, 2 cards at a time. We'll get to 5 and 7, but starting here. By the way, hopefully what I'm really teaching you is how not to gamble. Anyways. Yeah. Logan, can you read to me example 2, please? How many cards? Tree, I think. With replacement or without? Okay. Event A is talking about hearts, Logan. Event B, question B is talking about hearts, and C is talking about hearts. I think we can use the same tree for all of these. What would be a good letter to use for hearts? So you know what? How about this? H1, not H1. What is the 1 shorthand for on the first card? I'll figure it out if you use something like that, Chelsea. I'll puzzle it, okay? You don't need to list it. Oh, and then what would I use for a heart on the second card? You can have H2, not H2, H2, not H2. Hearts are red, so I'll use red. Ashley, how many hearts are there in the deck? Out of? How many non-hearts on this first level? Out of? Okay, let's fill in one branch. So down the left-hand branch, you picked a heart and you're holding on to it. How many hearts are now left in the deck? Out of? How many non-hearts? Down the right-hand branch, you didn't get a heart. You have no heart. Suspected that for a while. No. You have, okay, how many hearts are left in the deck? And? Julia, can you see where all those numbers came from? You're going to need to know a little bit about a deck of cards. And if you aren't familiar, please do, because card questions are, at least to me, inherently fun, because it's gambling, sort of, right? Is that okay, Bree? By the way, look up, look up, look up. Do these two branches, are they identical to those two branches? Oh, then this must be dependent. That's the easiest test for dependency. I glance at the tree and I say, oh, it matters which branch you went down at the top. It depends on which branch you went down at the top. It's dependent. There's other mathematical ways, but that's the cleanest. Okay. Both cards are hearts. What two numbers am I going to multiply? Oh, first of all, let's give you the notation. This would be heart 1 and heart 2. So that you get used to the workbook notation and it doesn't freak you out. Let's start writing that. How? Rachel, what numbers am I going to multiply here? 13 out of? And times, yep. Which is what? Oh, you did lowest terms already? So apparently it ends up being 1 out of 17. It's going to be out of 2652. 13 times 12 is going to be, well, 144 plus 12, 156 out of 2652, which I guess ends up being 1 out of 17. And again, though, I pause, Giancarlo. Had I asked you, hey, what are the odds? You're trying to get a flush in poker. What are the odds that your first two cards are a heart? I'm willing to bet you wouldn't have said, oh, it's going to be out of 17. That's not a number that, and again, Darian, we're only on our second card. Again, this is why people are such bad gamblers. This is why people are superstitious. Neither card is a heart. What am I multiplying here?
39 over 52 and 38 over 51.
Which is what? 19 out of 34?
Yeah.
19 out of 34, this is a fraction I can deal with. Are the odds bigger than 50% or less than 50% that I get no hearts in two cards? What would 50% be? What out of 34?
17.
17. So you know what? You got a better than even chance of getting no hearts. Okay. So if someone was saying, hey, I'll bet you that you get no hearts, I'd take that bet because I got a better than even chance of winning. And the more times I bet, the more likely it is that I'll come out ahead. Something called the law of large numbers and the gambler's fallacy, and it basically put those together, and it says, Logan, if the odds are in your favor, like 50.00001% even in your favor, keep playing, because the more you play, the longer you play, the more you'll slowly come out ahead. If the odds are not in your favor, even 49.9999%, the longer you play, the more guaranteed it is that you'll lose. In fact, there's a corollary to that, Jake, and it says this. If you're gambling and it's a game where the chance of winning is less than 50%, all of them, someone once asked, okay, what's the best strategy? And it turns out the best strategy is always take all of your money and bet it all at once. And the guy who wrote the paper, he finished off the paper and he says, it's true that anyone who does that feels like a fool. But anyone who does anything else is a far bigger fool. That's how he signed off the paper. Because the longer you play, if the odds are not in your favor, the more certain it is that you'll go broke. Trust me. It's been proven. C. What does C want? Which branches have one heart? And exactly one heart. Can you see there's two of them? You know what? Let's put a little check mark underneath those two branches, right? Is that okay, Mackenzie? Here's what it's going to be symbolically. And we're going to write this down just so you can see how it's yucky and why I like a tree. Symbolically, what you're saying is it's going to be heart on the first and not a heart on the second. Or not heart on the first and Hart on the second. Except Carson actually, or is, in fact, they could go this. Don't. That's too much to keep track of. This is why I started running away from the formulas. Even that is tough to keep track of. Look at the tree. It's the two middle branches. Mark, what does or mean? Put a plus sign. What does and mean? In fact, you know what the rule that we used to simplify this to? We used to say, you multiply down the tree, you add across the tree. It's going to be 13 out of 52 and 39 out of 51, or 39 out of 51 and, out of 52 and 13 out of 51. It turns out in this case, Taylor, each of these little mini fractions is the same because it's 13 times 39, 13 times 39 over 52 times 51, 52 times 51. So if you were really clever, you might have spotted that and just said, I'll do this times 2, but it's not always going to be that case. I can come up with more complicated trees. Anyways, what's the answer? Please do this. I'm deliberately using a different calculator because I want you to figure out how to use the fraction button on your calculator, and it seems like people are just copying off of me. So I'm using my TI, which does fractions differently from your Casios. Should end up with 13 out of 34 in lowest terms. We're going to finish with D. Rachel, what is, sorry, caught you. What does D want? First of all, 2 aces in a row. Good hand or bad hand? So I'm expecting a small probability or a big probability? Probably small. Okay, but anyways, what does it want? Okay. I could draw the tree, but we're going to stop. Let's see if we can't just visualize that single branch. That single branch would look like this. Right? Hey, if you want to. Okay. Here we're going to be really lazy and just draw that single branch, which means my built-in error check I'm not going to be able to fall back on. How many aces are there in the deck? Out of? You just picked one. How many aces are now in the deck? Out of? And in fact, some of you may say, you know what, Mr. Dueck, I think I could have done that even without drawing the tree by imagining the tree. Yeah, maybe. I can, if it's the same event over and over and over, I can keep track of that. It's going to be, which is what? Sorry?
1 over 220.
We're going to pause here. Just give me 1 second.